Morning, everybody.
Hi, I'm Chris Day. I'm from a company called Jaltek. We are a product development and contract manufacturer. So we've been trading in the design side of the business, which I started in 1987. That's for 36 years. On the production side, again, part of the same organisation. They started in 98, so about 25 years, 23 years. We work in many market sectors. And 20,000 square foot production facilities in Luton. But today I've sort of focus on some work we've done using flexible circuits in sort of space applications. And as technical director, I tend to get involved in all of the space and in fact all of the design projects from an early stage, chatting to people and bringing technology to people. Okay. Bit of heritage, really. We've been designing boards for space applications since, about 17 to 20 years. Started on a project called Beppe Colombo, which was a spacecraft mission to Mercury. That project was the first time that we looked at using Flexies. So I went into the customer at the time there, which we've been working with. Sat and looked at the project and he said, right, we've got 26 boards to design, circuit boards to design in about 6 months. And I said, well, actually, this isn't really the space project, and it's much faster than that. In space, we tend to get 2 or 3 years and go through a quite regimented process at the time. He said, but you've got to get to a proof of principle really quickly. So we started talking about what they were trying to do. And they had massive concerns, as with every application on spacecraft, with weight and size and all those sorts of things. So we talked about how he was going to construct his boards. And the reason he had so many different board types is he was stacking boards of about this sort of size and length, one on top of the other. Vertical boards, and then putting end boards to actually transfer the signals between them, etc. And I said to him at the time, I said, have you considered using a flex rigid for this? I said, it's not regularly used in space, but we thought about it. And we talked through the principles of what it might do. And then that was on the Thursday. And then I went home, etc. Came into work on the Monday to an email from him. And literally sat at his kitchen table on the Sunday afternoon, and he cut up cardboard and got some tape and said to me, is this what you mean? All right, so I've got the real one here. Okay. And like every good engineer, I've got a few spare bits left at home. All right. But it was exactly what we meant. So at that time, these ended up being 12-layer boards with just a single two-layer flex through the centre, and meant that we folded the boards then into this arrangement, which took away all of the vertical mount connectors, took away the end boards that he was going to use, etc. Added a massive level of reliability and ruggedness to the process, because the flex is a lot more rugged than like 3 solder joints. So you've got 2 solder joints on the connectors, and the connectors plug it into each other, and by vibration they're going to go through. So we took out weight, added reliability, and added up a much higher level of process. So that's the first time we've got Flexies in space. Since then, we've worked on a number of other projects. And this is just an example of sort of satellites and the applications where we've worked on the circuit board design and involved in early sort of discussions on material usage and construction and everything for the boards within that process. So I'm not going to run through any real depth for them. I've just put it there just to understand a little bit of how the history of where we've worked. I've then just done a little bit about some Flexies that we've put into current projects. So this is a project we did last year. It's still in its prototype stage as a CubeSat. We were involved right from the off, where we did a lot of consultancy on the product specification, how they were going to implement the circuit board, how they, with regards to the hardware development, the circuit board design, etc. Took it through all the component engineering, We also did all the enclosure development on this one for the client, so we developed the CubeSat, obviously off-the-shelf parts for some, but all the thermal analysis then to sort out the heat sinking and then the mass analysis and also the vibration analysis around that. So we'd have gone through 2 or 3 little loops of this is how we think we're going to mount it within this CubeSat. Run the analysis, okay, there's a bit of vibration, we've got a hotspot coming up in a certain area, we need to change the heat sink arrangements, and again, back around the loop. So that's an example of a full product and a full process that we've gone through from the original concept with the customer. And it's currently in evaluation. So I think I've got some images of it folded, actually. So that's the actual, just an image of the enclosure, how it's mounted, and you can see here how that's folded in on the other side of the board. Then, been working fairly recently on a thing called CLIM, or Gaia CLIM, which is a climate control and atmospheric monitoring process. This has involved about 6 different boards for the client. We've done a lot of consultancy on how the process, the fold, things like bend radiuses on the boards. The next one's got more challenges, but big challenge with regards to component technology and how you route in out high-speed data boards. How do you manage impedance control across flexes between certain areas of the board? When mounted, when folded, how's that going to fit into the enclosure? And again, backwards and forwards with the mechanical design to say that once folded, this is how the two sections can bend. Tells you a little bit more about the process. Then there's Altius. Now this has got 13 boards in it, but this particular board is a really interesting one because it's got a very, unusually, but it's got a very, very high pin VGA on there. So with this board, we had to some rather extensive challenges with reaching close enough to the ESA specifications so that the 12C compliance in design of the board. It's got microwire technology, so it's laser drilled on the top side. It's also laser drilled flex rigid using substrates that they were not totally happy with, should we say. So we went through quite a number of routes and concerns and revisions of change of process with ESA within the project map itself. And it ended up as a 16-layer flex with 4 flex layers internally, which fold. And this folds, you consider it sort of folds up to a connector at the front. Those fold up. This folds down and goes underneath. The normal sort of things you'll have with regards to all the power circuitry and that folding away from the digital circuitry for EMC, all that type of consideration. And again, how that then fits in the final satellite and whether its mounting points. As you can see, there's extensive physical mounts because of the vibration requirements. So it's a really interesting one because it took a lot of loops to go round because we couldn't satisfy all of the ESA rules and the ESA requirements on this particular project. So then talk a little bit about how you do meet ESA rules. One of the things we do, whether we're doing a project that's linked to ESA or not, is we always design it as close to ESA as we can without having a cost or a timescale impact. And one of the biggest things to try and meet is 12C design rules. Partly because, in this instance, they don't actually, they don't lend themselves very well to flexes. So, this is just a snapshot of a spreadsheet that we put together to work with the ESA rules. When you run through the standard, it comes down to about 38 different rules that you've got to try and match and work to and comply with. I've got it in the spreadsheet, which...
It's not coming up. It did come early, isn't it?
That's it.
No, it's not playing. Yeah. Down.
Sorry, Douglas.
Start, yeah. What's the
Believe it or not, it was tested before we started.
Yes, and you can see it. I'll just talk about it, and if it pops up, then we'll see. Basically, there's 38 different rules within the ESA standard when you're trying to match to a PCB physical construction. And those rules are, numbers or blocks of them are completely interrelated. So, as an example, if you're drilling a via, then your via size is generally driven by your component packaging technology. So you've got to go smaller. Then there's an aspect ratio that you've got to meet between the finished bore thickness and the size of the hole. But you've also got to have a certain pad size, subject to oversized by, I think it's about 35 microns, radius on the actual finished drill size. So trying to match a small component package with the hole size, then you find that you've got to have more layers because the impedance control is too high. So you can't use the same hole size because the aspect ratio then is too high. So they all interrelate. I'm more than happy to sort of share and discuss this in more depth. So what we did, we spent quite a lot of time basically going through the standard and preparing the spreadsheet that we actually fill out for every single layout that we do that's anywhere near an ESA project. Even if one day, not originally, many projects we've done, we always get, it could be used in an ESA project in the future. So what we do is we run through, we go through all of those rules with every single design. We put down what we believe it's going to be when we start the project, and we put down what it is at the end of the project. And if it doesn't comply, we put the reason why. And as I say, just understanding and getting through that matrix of rules, it can be fun. But if anybody wants to see a copy of it, please come and ask me afterwards. I'm more than happy to send it to you.
Not quite sure what happened.
All right, but no problem.
Definitely
If there's any questions, I'm more than happy to answer them. Thank you.